Hello statistics students, my name is Jamie Amy and this video will start our discussion on section 6.3 as well as discuss 6.4. Title, Sampling Distributions and Estimators. We've talked about population parameters versus sample statistics, and what I want you guys to do right now is test yourself. How many symbols can you write in? So you've got 1, 2, 3, 4 over here, the statistics or the sample, and 1, 2, 3, 4 more over here for the parameters from the population. Pause the video and try to write in as many symbols as you can. Welcome back. Let's see how you did. If you put X bar for sample mean and mu for population mean, you got them right. If you put lowercase s for sample standard deviation and lowercase sigma for the population standard deviation, nice job. Sample variance would then just be that squared, and population variance would be that squared. And the last two, if you didn't get them, that's okay. We haven't talked about these. The sample proportion, we're going to use a lowercase p with a hat on top of it. The hat represents it comes from a sample. And for population proportion, we'll do the p without the hat. All right, you guys, these statistics right here, we like to use these to target the parameters, okay, the population parameters. But we can't do that for everything we calculate. But these ones here, we're good. Here's what I mean. Sample means, variance, and proportions, they're what we call unbiased estimators. We can use those. They will target the population parameter. So you can use X bar to target mu. Same with S squared and P hat. Notice standard deviation is not listed here. There's a reason why. Things like medians, ranges, and even the standard deviation, they're considered bias estimators, so they do not target the population parameter. However, the bias with standard deviations is very small, so we will use that to target the population standard deviation sigma. Okay. And that's pretty much it for 6.3. Got to know which ones are unbiased estimators and which ones are biased estimators. Moving to 6.4, title is the Central Limit Theorem, or CLT for short. I like to teach the Central Limit Theorem through an example first, then we'll watch a little video, and then I'll show you the formal theorem. All right, so let's talk about this. An elevator capacity is 16 passengers and 2,500 pounds. Note that 2,500 divided by 16 is 156.25. If all passengers are male, what is the probability of exceeding the weight limit? A. Find the probability that one randomly selected male weighs more than 156.25 pounds. Males' weights have a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Okay, we've done problems like this one before. This one does not require the central limit theorem, just requires our normal distribution information. It says males' weights are normally distributed, which is what allows us to draw this bell-shaped curve. Gave us a mean, and a standard deviation as well. Standard deviation's here, mean is here. We're being asked if one randomly selected male weighs more than 156.25 pounds. So we're going to put that here. No central limit theorem required for this one. Part B is going to require it, and we're going to build up to that. We're being asked about that one randomly selected male weighing more than 156.25. So we need to use our normal calculator. We're setting it up with the requested probability that one randomly selected male has a weight greater than or equal to 156.25. Let's get... Okay, here we are in StatCrunch. Stat calculators, let's find that normal calculator. My advice is to clear everything out. Mean weight was 182.9, I believe. Standard deviation was 40.8. And we were being asked the probability that one randomly selected male weighs more than 156.25. Okay, remember when you hit compute, you're going to check two things. First, look at the graph. Does it look like the one you sketched? And then look at the answer, which is going to be populated here. First thing, graph looks good. Shading is on the right side, bell-shaped curve. And so our answer is going to be right here. We're going to take 4 decimals of accuracy, 0.7432. Let's see what that looks like in our... All right, that will give us our answer here. So the probability of randomly selecting one male and then weighing more than 156.25 is 0.7432. Nothing new in part A. We've done that before. It's part B that something changes. Read the question with me. Find the probability that a group of 16 males have a mean weight greater than 156.25. Here's the change, you guys. It's not just about randomly selecting one male. It's about selecting groups. Our group is of size 16. The question is about means, and the group is of size not equal to 1. And these two things combined are what inform us that we need to use the central limit theorem. Okay, I'm going to show you how to do that first before the video and the actual theorem. The central limit theorem is applied to problems about means that have a sample size not equal to 1, just like this problem. So what we have to do is take the standard deviation. We have to change that from sigma to sigma over the square root of this new sample size. That would be our 40.8 divided by the square root of 16. Okay, so when we go to our normal calculator and we set it up, we need to make sure we're having sigma, not the 40.8. We need to adjust it. It needs to be 40.8 divided by the square root of 16. Let's see what that'll look like. Okay, we're back in StatCrunch, and we are going to make one adjustment, just one, okay? It's right here. It's the standard deviation sigma. We have 40.8 there. We've got to change that. Okay, so I'm going to just use the calculator on my phone here. You guys can do the same. Any calculator will do. All right, we're typing in 40.8. But remember, we need to adjust that. We need to divide it by the square root of 16. Okay, so get that typed in your calculator, hit enter, and what the central limit theorem does is it adjusts the standard deviation. Ours changes from 40.8 to 10.2. Okay, now watch what happens when we hit compute. We have a new probability of 0.9955. The graph still looks accurate. Way over here at 156.25. It's still shaded on the correct side. But check out the answer. The probability has increased extremely. We're at 0.9955. All right, let's go back to our notes and talk about that. Okay, our probability went from 0.7432 to now the probability that the elevator is over the weight limit is 0.9955. Okay, what I want you to get from this is the computation part was quite easy. You already used the central limit theorem and you don't even really know what it is yet. All you have to do is recognize that the question is about means and you have a group larger than 1, and therefore you take that standard deviation and you adjust it. You adjust it by dividing it by the square root of the group size. All right, let's watch a little video that explains it in quite a different way, and then I'll show you the actual theorem.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average, and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group, so he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables, even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Puthikrit Bhattacharya. This video was created by Shui Cho and brought to you by CreatureCast. Special thanks to Casey Dunn. For more stories, visit creaturecast.org.
All right, so we've seen an example, a video, and now let's check out the central limit theorem. If 1 and 2 are true, we need random variable x has any distribution with a mean of mu, standard deviation of sigma. 2, we need simple random samples, all of size n, and is not equal to 1, are selected. Then 3, 4, and 5 follow. 3, as the sample size n increases, the distribution of sample means approaches a normal distribution. That is, it becomes a bell-shaped curve. 4, the mean of the sample means is the population mean. That was section 6.3. The sample mean targets population mean, so don't change it. Leave the sample mean, but do change the standard deviation. That needs to change to sigma divided by the square root of the group size. So to apply the central limit theorem, divide the standard deviation sigma by the square root of the sample size radical n. All right, so we've seen an example, a video, and here is the formal central limit theorem. Let's try one. All right, try this example. The length of time it takes to play an NBA game is normally distributed with a mean of 137 minutes and a standard deviation of 11 minutes. 50 game times are randomly selected. Find the probability that the sample mean is between 120 and 135 minutes. All right, pause the video, open StatCrunch, give this one a try, and a hint, make sure you switch it to between. Welcome back. Let's see how you did. If you recognize that this problem is about means and the sample size is 50, so it's not 1, then we need to apply the central limit theorem. Then you would have adjusted that standard deviation from 11 minutes to 11 minutes divided by the square root of 50. And make sure on StatCrunch you select that between option, so it will give you the probability of, and it'll give you 2 cells, fill them in with 120 and 135. Run that program correctly and we'll get 0.0992. Asked, what percent of NBA games are between 2 hours and 2 hours and 15 minutes? That's 120 minutes and 135 minutes, by the way. And we're asked to round to the nearest percent. So that would be right here. We take this 0.099, move that decimal twice, same thing as multiplying by 100, and then round to the nearest percent, which would be 10%. So it turns out about 10% of games, NBA games are between 2 hours and 2 hours and 15 minutes. All right. Next video will be on Chapter 7, Confidence Intervals. Thank you for being here. My name is Jamie Amy, and I will see you soon.